Picture a world where the sky shimmers in a different shade of blue, where oceans plunge endlessly deep and gravity tugs at you with twice the force you feel right now. Imagine a place so remarkably like home that we've dared to name it Earth 2.0. But how long would it actually take us to reach this potential new world? This is Kepler-22b, NASA's poster child for the search for extraterrestrial life. It's out there right now, orbiting its star, perhaps harboring clouds, rain, maybe even something alive looking back at us. But there's a problem, a massive silent problem that most headlines ignore when talking about new Earths. The problem is the abyss. The distance is so vast that if you climbed into humanity's fastest spacecraft today, you'd die before completing 1% of the journey. Your grandchildren would die. Entire civilizations would collapse and be reborn, and that ship would still be drifting through emptiness. Today, we're calculating exactly how long it would take to reach Kepler-22b using current technology, and exploring what would be necessary for human to one day actually set foot on that alien ground. Before we chart our course, we need to understand why this destination deserves the risk. Why Kepler-22b when the universe is cluttered with countless floating rocks? This exoplanet is special, nestled in the constellation Cygnus, the Swan. Kepler-22b earned the distinction of being the first planet confirmed by NASA's Kepler telescope, orbiting squarely inside the habitable zone of a Sun-like star. The habitable zone, affectionately called the Goldilocks zone, is that precious region of space where conditions are just right. Not so close to the star that water boils away into steam, not so far that it freezes solid into ice. It's the sweet spot where liquid water, the essential ingredient for life as we understand it, can pool on a planet's surface. Kepler-22b's star is a G-type yellow dwarf, strikingly similar to our own Sun, just slightly smaller and cooler. This means the light washing over that world has a familiar quality, the kind of light our eyes evolved under. But the similarities end there. Kepler-22b is what astronomers call a super-Earth. It measures roughly 2.4 times Earth's radius. And here's where the mystery deepens, the mystery that keeps planetary scientists awake at night. We don't know what it's made of. With this size, it could be a colossal rocky world bearing massive mountains and sprawling continents, or it might be an ocean planet, blanketed entirely by a sea hundreds of miles deep without a single patch of dry land. Or worse for our hopes, it could be a mini Neptune, a rocky core smothered beneath a crushing atmosphere of toxic gases, where the pressure would flatten any visitor instantly. Despite uncertainty, the possibility of a temperate world with water is enough to ignite our imagination. If life exists there, it's had billions of years to evolve. The potential reward is staggering, but the price of admission is the distance. If you enjoy deep, evidence-based space discoveries, be sure to subscribe and turn on notifications so you won't miss what's coming next. Kepler-22b sits approximately 600 to 635 light-years from Earth. Written like that, 600 sounds manageable. You might drive 375 miles to visit family on a weekend. But in space, light-years isn't a measurement of time. It's a measurement of distance. Staggering, incomprehensible distance. A light-year represents the distance light travels through vacuum in one Earth year. Light moves at 186,282 miles per second. In the blink of an eye, a photon could lap around Earth's equator more than 7 times. Let's establish perspective. Light takes roughly 1.3 seconds to reach the Moon from Earth. It takes 8 minutes to span the 93 million miles between us and the Sun. To traverse our entire solar system out to Pluto's orbit, light requires about 5.5 hours. Now absorb this. The light that departed Kepler-22b, the light NASA's telescope captured, began its journey when the Middle Ages were ending in Europe. When Christopher Columbus set sail for the Americas, that light had already been traveling for nearly a century. In miles, that's approximately 3.5 quadrillion miles. An abyss our human minds simply cannot process, but our mathematics can. Let's say we decided to launch today. We assembled the brightest engineers from NASA, SpaceX, ESA, and constructed a spacecraft using the most advanced propulsion systems currently operational. Forget your car cruising at 62 miles per hour, which would require 6 billion years to reach Kepler-22b. The fastest object humanity has ever built is the Parker Solar Probe. Harnessing the sun's gravity to accelerate, it reaches absurd velocities, approaching 430,000 miles per hour during its closest approaches. But that's essentially cheating. It's falling toward the sun, not cruising through interstellar space. Let's use something actively leaving the solar system. Voyager 1 launched in 1977. It's currently traveling at roughly 38,000 miles per hour. That's fast. Fast enough to cross the entire United States in just minutes. If we aimed a spacecraft with Voyager 1's velocity directly at Kepler-22b, how long would the journey take? Remember, light itself needs 600 years. Voyager travels at a minuscule fraction of light speed, approximately 0.006% to be precise. Running the calculations to cover 600 light years at 38,000 miles per hour, the voyage would consume approximately 10 to 11 million years. 10 million years ago, modern humans didn't exist. If we'd launched then, it would arrive only now. With chemical rockets, the trip is impossible. Wait, hold on. Before you close this video thinking interstellar travel is hopeless, before you decide this dream is dead, let me show you something. Because here's where it gets genuinely interesting. We're not stuck with chemical rockets forever. Humanity has other ideas. Radical ideas. Ideas that sound like science fiction, but are grounded in real physics. So stick with me, because the next technologies we're about to explore, they change everything. If we can't travel faster with chemical rockets, maybe we need to embrace different physics. Let's explore technologies that exist beyond blueprints. Technologies scientists are actively researching. Nuclear pulse propulsion. Imagine a spacecraft propelled by detonating small nuclear bombs behind it. Each explosion carries a shock wave that pushes the vessel forward. This concept, called Project Orion in the 1960s, could theoretically reach 3% to 5% the speed of light. At 5% light speed, Kepler-22b becomes reachable in roughly 12,000 years. Still impossibly long for a human lifetime. But now we're talking about timescales for generation ships. Vessels carrying multiple generations start becoming theoretically feasible. Nuclear fusion propulsion takes it further. Instead of explosions, we harness the power of the sun itself, fusing hydrogen atoms to release tremendous energy. Fusion rockets could potentially reach 10% the speed of light. This cuts the journey to Kepler-22b down to approximately 6,000 years. 6,000 years ago, humans were just inventing writing, building the first cities. It's still generational, but now we're approaching timescales where advanced civilizations could plausibly maintain continuity. Antimatter propulsion pushes into true science fiction territory. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into pure energy. It's the most efficient fuel theoretically possible. Antimatter engines could accelerate spacecraft to 50% light speed or higher. At 50% light speed, Kepler-22b sits just 1,200 years away. Now we're in the realm where a sufficiently advanced civilization with suspended animation or extreme longevity could conceivably make the journey within a few generations. But there's a monumental problem. Producing antimatter is incredibly expensive and energy intensive. Currently, we can create only tiny amounts at particle accelerators, nowhere near enough to fuel a starship. But the physics works. It's a question of engineering and scale. Now we enter pure speculation, the kind that makes physicists simultaneously excited and skeptical. What if we didn't have to travel through space at all? What if we could bend space itself? The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, suggests we could create a bubble of warped space-time around the spacecraft. The bubble would contract space in front of the ship and expand it behind, effectively allowing the vessel to surf through space faster than light without technically violating Einstein's laws. If, and this is a cosmic if, we ever developed a functioning warp drive, Kepler-22b could theoretically become reachable in years, maybe even months, depending on how fast we could manipulate space-time. But here's reality crashing back in. The Alcubierre drive requires exotic matter with negative mass, something we've never observed and might not exist. It would need energy equivalent to the mass of Jupiter or more. It's mathematically possible, but practically, as of now, science fiction. So what's the honest answer to our question? How long would it take to reach Kepler-22b? With today's technology, using our fastest spacecraft like Voyager 1, the journey requires 10 to 11 million years. Impossible for any individual, any generation, any civilization resembling ours. With advanced nuclear propulsion, we could develop within a century or two. We're looking at 6,000 to 12,000 years, still multi-generational, requiring massive ships carrying entire societies, massive resources, unshakable commitment across centuries. With theoretical antimatter engines, assuming we solve production challenges, maybe 1,200 years with advanced life support or suspended animation. And with speculative warp technology, unknown. Possibly years, but requiring physics breakthroughs we can't even properly imagine yet. Kepler-22b isn't just distant. It represents a fundamental barrier to human exploration. The galaxy is vast beyond comprehension, and we are, for now, confined to our tiny corner of it. But here's what's beautiful about this impossibility. Knowing the true scale doesn't diminish our wonder, it amplifies it. Every photon that reaches us from that world traveled for 6 centuries, crossing an abyss so enormous it defies intuition. And yet we caught it. We analyzed it. We learned from it. That alone is extraordinary. Maybe Kepler-22b remains forever out of reach. Maybe it stays a dream. A motivation, a reminder of how small we are and how much further we have to go. But you know what? There's another destination, one much closer, one we could actually reach in our lifetimes: Mars. So, if 10 million years to Kepler-22b sounds discouraging, let me show you something more hopeful. Check out my video, How Long Would It Take Us to Go to Mars?, where we break down the actual journey times, the launch windows, the technology we're using right now, and why you might see humans walking on Martian soil within your lifetime. Click now, because this journey, it's actually happening.